It is, yeah.
I can't tell that way. Hey, look at that, it's working. Okay. So, he understood, Kepler was able to figure out how the planets move and was able to help build the solar system. Sir Isaac Newton is going to talk about gravity and actually why the planets are staying in orbit. And what he realized was that gravity is what keeps everything in orbit. Just like objects fall to the Earth here, things that are in orbit, okay, or even talking about the moon is falling to the Earth just like the apple is, except the moon is going to be falling around the Earth. I'm going to talk with what that means in a bit. But the formula he came up with for gravity was this. Force of gravity, any gravity, will be equal to G, which is the new number you need to know. 6.67 times 10 to the negative 11. Times the mass of one object, times the mass of the other object, divided by the distance the two objects are between each other. R just stands for distance, just like radius. Okay? So, no matter what, any two objects that have mass have gravity. Okay, so the sun and the Earth have gravity pulling them between because they have mass. But any other objects actually have gravity. Okay? The stapler and the scissors have a gravitational force of attraction between them. Okay, now why is it that they don't fly towards each other? Because of this little number, 6.67 times 10 to the negative 11. I want you to think about what that number is. 6.67 times 10 to the negative 11 is a 6. You gotta be kidding me.
That's great. That's a little bit awkward.
That is awkward.
Awkward moment.
Maybe if I do this, I can get to it.
Let's go to awkward moment.
Let me pause for a second. We'll pause for... We're back. Okay. 6.67 times 10 to the negative 11 is really a 6.67, and then negative 11th means 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's a really small number, right? Point, and then 10 zeros, and then 667. That's an extremely small number. That's why, so anything that has any mass does have a force of gravitational attraction. Okay? Two objects, these have mass, they do have gravity. But the problem is the force of attraction, or the mass, is so small that you're going to have to multiply it by that number. You're never going to notice it. It's not like you even could walk by a skyscraper and all of a sudden get pulled next to it. Alright? It has to be a mass of something so extremely large, like a planet, that you would ever notice gravity. I mean, you feel the gravity right now. Okay? You feel your butt in the chair. You're feeling the force of gravity. And that's with a planet. That's with the Earth. Okay? So anything smaller than that you won't notice, but it's there. And that's the big idea you need to understand. Okay? Any object with mass, or any two objects with mass, will have a force of attraction. Okay, guys, we're looking for that new pickup line. That really wouldn't help you at all, but, you know, decide. Okay, now, so remember that number, 6.67 times 10 to the 11. You'll need to know how to use this in your calculator, okay? In your calculator, if you have a TI, you're going to see the little comma button, and then you're going to see 2 capital E's next to it on top. That's what you want to do scientific notation. If you have the crappy Casio, it's going to be an EXP button. You'll see that EXP button. Okay? And the way you're going to, because now we're going to have these ridiculously large or ridiculously small numbers. And to figure out how to plug in the calculator or to get answers, you're going to have that E. We talked about it before. But you're going to have that E button. So when you plug in something, you're going to say 6, 0.67, and then E, -11. And the way you're going to put that in is 6.67, shift, and then the comma to get that double E, which will give you that, times 10 to the -11. That's what it'll need to look like. Okay? Okay. Now, moving on. This is why, again, the apple and the moon, an object falling to the ground is just like the moon orbiting, or a satellite. When you have astronauts that go up in space, okay, they say they're in zero gravity. It's not actually zero gravity. They're not out in the far reaches of space where gravity isn't a factor. Astronauts are probably only about here, above the Earth. Okay? They're not far enough away from the Earth where the distance actually matters. Alright, going back to the equation real quick. Here, the distance is important. Okay? The further away two objects are, the less and less the gravity is. If you buried down and got close to the center of the Earth, the force of gravity would be extremely high. It would get stronger and stronger and stronger the deeper you got. In fact, because it's squared, if you went halfway down towards the center of the Earth, it would be 4 times stronger. The gravity you would feel would be 4 times the strength here. So the distance apart does have a factor in it. Okay? But where astronauts are, just above the surface of the Earth, or a little bit above it, even if it's outside the atmosphere, is not strong enough so that gravity is gone. They have just as much gravity, or almost as much gravity. The idea is this, okay? Let's say that we know that, the Earth is round, but to us, it feels flat, because the Earth is so large compared to us. Alright, so you throw a ball and you know it's going to fall down, right? You throw a ball a little bit faster, it's going to go a little bit further, and then fall down. And then a little bit faster, and a little bit faster. Well, the same idea is here. So if I throw a ball really, really fast, it might go that far. It really couldn't go that far, but if I had rocket boosters on that baseball, all right, I throw it a little bit faster, it's going to go a little bit further, and sooner or later it would hit the ground, but the Earth is going to start curving away. So what astronauts are doing is this. They go up a little bit, and then if you've ever seen a launch, they roll over on their side. A space shuttle shoots up to a certain height and then rolls over. They go up to a certain height so they can clear all the mountains and everything else. And then they roll their sides and use most of their rocket fuel to propel them as fast as they can go horizontally, just like the baseball. And the idea is that if they can go fast enough that they're going to fall. There's still gravity. Okay? They're still going to have to keep falling towards the Earth. But if they can go fast enough, sooner or later, the Earth is going to keep curving away from them as it keeps falling. And so every time it tries to hit the ground, they're going so fast horizontally that the Earth just keeps curving away. That is what we call orbit. That is what astronauts do. Astronauts feel almost as much gravity here as we do on Earth. But because they're going so fast horizontally, the Earth just keeps curving away from them. Does that make sense? No? Maybe? This is how fast they have to go. 17,285 miles an hour. If they can go 17,285 miles an hour horizontally, whenever they want to fall and hit the ground, the Earth is going to just keep curving away as much as they fall. So that's what astronauts do. They keep falling. Ever go a little too fast over a hill and you kind of feel that little weightlessness in your stomach? That's what astronauts feel. The only difference is you hit the ground, okay, and they just keep falling. Alright?
That is awesome.
So they feel as much gravity.
Well, it's a roller coaster ride.
It's not that far of a distance between where we are and where they are. But that's it. So the way you can get that feeling, the astronauts train on an airplane that is, I think it's called a DC-130. It's a big, huge plane. And in the cargo bay, they set it up and have all these pads around it. And what they do is they fly up really high, and then they shoot down. Okay, and they give that free fall. And so then for that split second, the astronauts are floating around in weightlessness. And what I'm telling you is that's not a simulation. That is exactly what astronauts are experiencing. The only thing with astronauts is they're so far up there and they're going so fast that they never actually are going to stop falling. They just keep falling the entire time. Okay? There's nothing here on Earth that can, there's no chamber where you can flick a switch and then they turn off gravity and you can float around. That doesn't happen. That's impossible. Some student during second period asked if you put a vacuum in it. No, you can't. You can't turn off gravity here on Earth. Okay? Astronauts are just in free fall. They just keep falling. But they're going so fast horizontally, 17,285 miles an hour, that the Earth keeps curving away from them as they fall. And they never hit the ground. Cool, huh? Now I'm going to talk about Apollo 13. I'm going to show the behind the scenes part of it. In Apollo 13, you see some scenes where they're like just a waist up and you see them doing this, right? And really all they're doing is this. Okay, they're just acting and pretending to be floating around. But you do see in scenes in Apollo 13 where like they have, like you've seen the pictures of astronauts where they have water floating around like in a big bubble and they throw the food to each other and all that. They're able to do that in Apollo 13 too. And the way they did that was they put the movie set inside the airplane. And so you'll see these scenes where they actually have like, the juice floating across the screen and all that stuff, them floating. That's not strings, that's them in an airplane so they could do it. Yes, sir?
Are we going to need that?
Nope, you don't need that data. I just wanted to show you that. Make you smarter. Okay, any questions on this? Alright, we will pause it, or we're done there.